All right, let's jump right in. Today we're going to talk about a group of chemical compounds that are, well, they're pretty much everywhere. They can literally save your life, but they can also be responsible for some pretty nasty smells. So let's dive into the fascinating world of amines.
So here's a weird one for you. What in the world could a life-saving shot and, a decaying fish possibly have in common? I know, it sounds like the setup for a really bad riddle. You've got this amazing medical tool on one side and this, really awful smell on the other. So what's the link?
The answer, it's a family of chemicals called the amines. That's it. Epinephrine, the stuff in an EpiPen that can stop a fatal allergic reaction in its tracks, that's an amine. And then you have a compound like cadaverine, which, the name kind of gives it away. It's what causes that horrible smell of decay. So right there, you see this wild split personality. Amines are at the very heart of both life and death.
So today, we're going to dig into the story of these compounds. We'll see how their whole chemical identity, which is all built around one little nitrogen atom, makes them these major players in our world.
Okay, here's the plan. First, we'll get to know the amine family, see what they're made of. Then, we'll figure out where they get all their chemical power from. And finally, we'll look at how they show up everywhere, from your medicine cabinet to the factory floor.
So let's get down to basics. What actually is an amine? Well, the blueprint for every single one of them starts with something you've probably heard of, ammonia. Think of it like this. An amine is basically a modified ammonia molecule. You start with good old ammonia, that's one nitrogen atom with 3 hydrogens attached. Then you just pop off 1 or 2 or even all 3 of those hydrogens and stick on a carbon-based group instead. That's the whole game. And that one simple move is what creates this massive, super diverse family of chemicals. And that leads us right into how we sort them, which is actually super straightforward. It's all about counting how many hydrogens got swapped out. So if you only replace 1 hydrogen with a carbon group, you've got yourself a primary amine. See? There are still 2 hydrogens hanging out on that nitrogen.
Makes sense, right? So what happens if you swap out a second one? You get a secondary amine. Now that nitrogen is holding on to 2 carbon groups and has only 1 hydrogen left. And you can probably guess what's next. Swap out all 3 hydrogens and boom, you've got a tertiary amine. And notice there are 0 hydrogens left directly on the nitrogen. So that's it. Primary, secondary, tertiary. It's just counting. 1, 2, or 3 carbon groups attached to that nitrogen. Simple as that. Let's make this real with a few examples. We start with methanamine, a primary amine. Now, if we stick another carbon group on there, it becomes a secondary amine. And if we add a third, it becomes a tertiary amine. It's like a little ladder. And it's not just simple chains. Look at aniline. That's a primary amine too, but its nitrogen is attached to a completely different structure, a benzene ring.
And this brings us right back to that smell. A lot of these smaller amines have really strong and often, let's be honest, pretty unpleasant odors. In fact, that tertiary amine we just saw, trimethylamine, that is literally the chemical that gives decaying fish that infamous fishy smell. It's what gets released when proteins start to break down. Okay, so we know what they look like, but why are they so reactive? What's their secret sauce? What gives them this chemical personality that lets them be both a life-saving drug and the reason you throw out old fish?
Well, the secret is hiding in plain sight, right there on the nitrogen atom itself. It has this thing called a lone pair of electrons. Now, these 2 electrons, they aren't tied up in any bonds, so they're kind of available. They're just sitting there, ready and waiting to react with something. And that is what makes amines so powerful. It's why they act as bases and why they're always looking to get in on some chemical action. That lone pair is their superpower.
And that superpower doesn't just affect how they react. It changes their physical properties in a huge way. Just look at this. We have 3 different amines here. They all have the exact same atoms, just arranged differently. But check out their boiling points. It's wild. The primary one boils at almost 50 degrees Celsius, but the tertiary one, it boils at just 3 degrees. How is that even possible?
The whole difference comes down to one thing, hydrogen bonds.
See, primary and secondary amines still have those hydrogens attached to the nitrogen. This lets them form these really strong connections with each other. It's like they're covered in tiny molecular Velcro. They're very sticky. But tertiary amines, they don't have any of those hydrogens on the nitrogen, so no Velcro. They don't stick together nearly as well. That's why it takes way less energy, way less heat, to get them to fly apart and turn into a gas.
All right, so we've got the chemistry down. Now for the fun part. Let's see where these things actually show up in our world. Because all that reactivity we just talked about, it makes them one of the most useful tools in the entire chemical toolbox. And I mean it. They're a real chemical jack of all trades. The bright colors in your clothes? A lot of those dyes get their start from amines. You know natural gas? They use amines to clean it up, to literally sweeten it by pulling out all the junk. And hey, if you've ever used that two-part epoxy glue, the hardener part, that's almost certainly an amine. It's what reacts to make the whole thing cure into that super strong solid. But maybe the biggest deal of all is in medicine. This is just incredible. A major scientific journal found that most drugs, the ones we have now and the ones being developed for the future, contain amine groups. Think about that for a second. Their special ability to interact with the molecules in our bodies just makes them absolutely essential.
And you have definitely come across these yourself. Ever taken an antihistamine like chlorphenamine for allergies? That's an amine. A decongestant like ephedrine to clear your nose? That's an amine. Even major drugs like antidepressants and powerful painkillers like morphine and codeine. Yep, all amines. Every single one of them uses its unique structure to do a very specific and very important job in our bodies.
So when you put it all together, you start to realize these things are everywhere. But they're kind of hidden in plain sight. From the chemistry inside our own cells to the medicines that heal us and the materials that build our world, amines are like the secret architects of modern life. They're the busy, reactive workhorses doing all the important jobs just under the surface.
It really makes you think, doesn't it? These compounds, which all start from that one simple ammonia molecule, are so woven into the fabric of our lives. It just makes you wonder, what else are they up to? What other critical things are they quietly building in our world that we don't even know about yet?